All right, so here we go. New stuff coming at you. We're starting to get a little bit of a handle on this precipitation. Certainly writing the equations is relatively easy once you've got the simple solubility rules down. You swap the partners, you look up the new stuff, okay? You got to memorize those solubility rules. That's an important thing of what you have to do, okay? Remember we said there were two other categories of reactions, okay? Today we're going to talk about acids and bases. Tomorrow we'll talk about oxidation reduction. That's another example of the precipitation in terms of rain. The word precipitation means one phase changing into another as coming out of solution, basically. So we have precipitation where we have aqueous, liquid dissolved in water turning into a solid. You can also have the gas phase of the water droplets, sort of gas phase, condensing and forming into a droplet that falls out of the solution. Essentially, clouds are like a solution of water and air. And so the precipitation is the water coming out. So it means the same thing. Okay, the first thing we have to do is we have to understand what are acids and bases. Okay, there are two primary definitions that we use. The first one, the simpler one, is what we call the Arrhenius definition of an acid and a base. Okay, and it's really simple. It says an acid produces hydrogen ions. An acid is a substance when dissolved in water produces hydrogen ions, and a base is a substance when dissolved in water that produces hydroxide ions. Okay, so something like HCl, hydrochloric acid. When I dissolve it into water, it splits apart to produce its ions. That's an acid. Okay, sodium hydroxide. Sodium hydroxide is a base. When I dissolve sodium hydroxide in the water, it splits apart and it produces hydroxide ions. Okay? So, acids produce hydrogen ions, bases produce hydroxide. That's the Arrhenius definition. Unfortunately, the world is not quite that simple. Okay? There's a lot of compounds like ammonia. When I dissolve ammonia into water, I get a solution that has hydroxide ions in it. But ammonia does not have hydroxide in it. It cannot give off hydroxide ions. So we have to have an expanded definition that will deal with these other compounds that function as bases, that can react as bases, but don't have hydroxide in them. And that definition is called the Bronsted-Lowry definition. Okay, named after the two guys who came up with it, Bronsted and Lowry. So, the internet is a marvelous place. So, Bronsted-Lowry definition says acids are substances that can donate protons. Notice it's a little different. It's a little more generic. We don't have to be in a water solution anymore. This can happen in other types of solutions. And the hydrogens can be transferred from one molecule to another, not free-floating. Bases accept protons. So hydroxide is a base. It can take in a proton to form water. That can happen. But ammonia would also be a base. We still have our same examples. We have our hydrochloric acid. That's still an acid. It meets these definitions. But now our ammonia can also function. Okay? If the hydrogen from the hydrochloric acid is given off, if the hydrochloric acid donates the proton to the ammonia, it forms ammonium. The ammonia, NH3, gained a hydrogen. That is what bases do. Bases gain hydrogens, protons. A hydrogen ion is a proton. They're the same thing. Okay? So this reaction has an acid and a base in it. But it does not meet the Arrhenius definition. Okay, we have our hydrochloric acid gives off a hydrogen to the ammonia to form ammonium. And the ammonia takes in a hydrogen to form the ammonium. Okay? Now, what's interesting about this is we call these, parts of these, we call them conjugate acid-base pairs. And the pair here, one of the pairs, is the ammonia and the ammonium. These two can go back and forth depending on what reaction we're talking about. If I were to take this reaction and flip it around, okay? If I reverse this reaction, now what's happening is the ammonium is giving off a hydrogen. The NH4 loses a hydrogen to become NH3. The NH4 is an acid. Acids give off hydrogens. NH3 is a base. Depending on which direction you're going, you have an acid and a base pair. We have two acid-base pairs here because this Cl- is actually functioning as a base in this backwards reaction. Okay? To figure out whether something is an acid or a base, you look for the transfer of the hydrogen. If the substance gains a hydrogen, it's a base. If the substance loses a hydrogen, it's an acid. It's that simple. If I'm going this direction, HCl gives off a hydrogen, NH3 gains it, and we become NH4 and Cl-. But when we're going backwards, the NH4 gives off a hydrogen, it functions as an acid. Cl- gains a hydrogen, functions as a base. So yeah, the acid, they're across, they're on opposite sides. The pairs are on opposite sides. So here's NH3 is a base, its conjugate acid is NH4 plus.
Okay.
Yeah. Yeah, pretty much, because if it loses a hydrogen, whatever's left is its conjugate, is its pair.
And then you said they donate protons. So don't protons, isn't that kind of hard to like take away protons?
Turns out, not really, because a hydrogen ion, H+, just a proton. Because it's lost its one electron. And the hydrogen atom is one proton and one electron, and that's it. So once you have the hydrogen ion, a hydrogen ion is a naked proton, just a proton all by itself. So when we write ammonia, we just put all the hydrogens together. Right? The ammonium is just all the hydrogens stuck together. But most acids, you write the hydrogen out in front. Conjugates are different. They don't follow a lot of the same conventions for how you write them as other substances. It depends a little bit. And ammonia is a kind of a special one, I think, too. Okay? Now, here's the thing. You know, I'm showing this as a reverse reaction. The truth is, this reaction would never happen in reverse because of what kind of acid HCl is. Okay? What we need to talk a little bit about is what we call the strength of the acids. It's highly related to what we call the strength of an electrolyte. Electrolytes are substances that dissolve into water and then produce ions that can conduct electricity. For water to conduct electricity, it needs to have ions in it. Water by itself doesn't conduct electricity very well at all. Okay? You need to have ions in it that carry the electrons around. That's what electricity is, moving electrons. So, a strong electrolyte is a substance that will dissociate and produce ions. Weak electrolytes don't break apart very well. Substances can dissolve into water and not break apart. That happens quite a bit. Covalent compounds do this all the time. Weak acids and weak bases are similar in that they dissolve into the water, but they do not separate into their individual ions. Okay? Strong acids and strong bases do separate. The prototypical, the most common weak acid is ethanoic acid. Okay? Ethanoic acid is similar, or another name for it is acetic acid. It's an older name. Ethanoic is its proper name. The common name is vinegar. Okay? So vinegar, this is the acid produced by bacteria, the yeast that are used in the fermentation to produce vinegar. C2H4O2. Okay? You'll also very commonly see this written slightly differently. You'll see it written a lot as This is the structure. So you'll see a lot like this. CH3COOH. That's a really common way to see it as well, and we'll see some of that as well in the problems that we're going to do. But that's the formula for ethanoic acid. I can get ethanoic acid to react with potassium hydroxide. Okay? What's going to happen is the hydroxide here is going to come, and it's literally going to pull this hydrogen off. It's going to rip it off of the molecule. Okay? And what I would have, and that reaction of the hydrogen with the hydroxide to produce water, that is our typical acid and base reaction. Okay? And then what we'll have left is the acetate ion, okay, and the potassium ion is what we would have left over. So here, this would be our molecular equation for an acid and base. Acids typically react with bases to produce water. The exception being any kind of ammonia compound, because ammonia doesn't have hydroxide in it. If your base has hydroxide, it's going to react to produce water. L stands for liquid. AQ stands for aqueous, which means dissolved in water. So the potassium hydroxide is dissolved. So these two started as solutions, 100 milliliters of each in a bunch of water. I mixed them together. I produced a tiny bit more water, and I had these guys floating around. Okay? The amount of water here produced in these reactions is going to be so small as to not significantly matter in general in terms of changing the volume. Not for our calculations, certainly. So now we have to think about the strength. This is what we would call the molecular equation. This is our acid and base reaction, an acid reacting with a base to produce water and some leftover stuff. We call this leftover stuff the salt. So in chemistry, salt means ionic compound, not sodium chloride. Okay? Now here's the thing. We know when I write complete or net ionic equations, what do I do with aqueous compounds? They're ionized. If they split into their ions, I write them separated. Acetic acid is a weak acid. It does not separate in water. We'll get there in just a sec. So I have to leave it stuck together. The potassium hydroxide, however, is a strong base. It completely separates. And our solubility rules tell us that too. Okay? This is a type of compound that can dissolve into water without separating. Just like sugar or ethanol. Other covalent compounds dissolve into water without separating. This is one of them. Okay? So potassium and acetate, these don't stick together. Alkali metals don't form solids. The water, of course, stays together. So my net ionic reaction would be the acetate reacting with the hydroxide. Potassium is going to be a spectator ion to produce acetate ions and water. Same structure, molecular, complete, net ionic equation. The difference is this thing doesn't break apart. And the key question, how in the world do we know whether it breaks apart or not? Because that seems to be really important for if we write it, how we write these things. And unfortunately, there's no easy way to know except to memorize. But here's what you do. Most acids are weak. If it's a weak acid, what does that tell me about breaking apart? It does not break apart. Weak acids are weak in how much they break apart. They do not break apart very much. Strong acids are strong in how much they break apart. They break apart a lot. Okay? These are the common strong acids that you need to memorize. Hydrochloric acid, sulfuric acid, nitric acid, hydrobromic, and perchloric. These are on the Mr. Glimmie sheet of things to remember, as are the solubility rules. These are strong acids. They break apart.
You said that there's like acid-base pairs. Is there any like relationship, like a strong acid and like a weak?
Yes, there is. We'll learn all about that second semester. Yes, there are very important relationships between the strength of the acid and the conjugates. You can assume that any acid other than this is a weak acid. There are a couple of other strong ones, but they're not important. They're not going to come up on a test. So you have this list. Make yourself some flashcards. Memorize these guys. Okay? Now, here's where we start to bring in chapter 3 stoichiometry stuff. Because these are all just chemical reactions. It's the same stoichiometry we've been doing. Okay? So let's look at how we can actually do these kind of reactions. We've done a bunch of calculations with precipitation. With acids and bases, there's just a special type of reaction, a special way to conduct the reaction. It's really just more of a method. It doesn't change the math, doesn't change what we're doing at all. It's just a way that we typically react acids and bases called titration. Here we have an Erlenmeyer flask. Okay, it's a conical flask. We've used them. I've had them up in class before. And what we're going to do to that flask, we're going to put in some sodium hydroxide. So I pour some sodium hydroxide solution into there. What I want to do is I want to say, hey, what's the concentration of that sodium hydroxide solution? And the way I can do that is I can take a burette. A burette is a device that allows us to very accurately measure out liquids. So it has a valve here that I can open and close and have drops go in. Okay? And what I'm going to drop in here is I'm going to drop in some hydrochloric acid. And now, the way that this works is, this is a strong base. So in the solution, what is it really? Is it sodium hydroxide stuck together? No. Strong base means it's actually sodium ions and hydroxide ions. This is hydrochloric acid. What kind of acid is that? Which means it's really separate ions. Now, when I drop in the hydrochloric acid, the hydrogen reacts with the hydroxide to produce water, and I'm left with sodium ions and chloride ions. Okay? That's sodium chloride, salt water. Okay? So, now, the key here is that when I'm doing this, when I'm conducting this type of chemical reaction, I can go ahead and determine a special point. I can use chemistry. I can use some indicators that will change color when the moles of acid equal the moles of base. We use N to represent moles because we use M to represent mass. So we use a lowercase m to represent grams, mass. Okay? So we use N, lowercase n, to represent moles. Now, because I can do some cool chemistry to figure out where this point is, I know that when I reach that point, if I know the volume and the molarity of this acid, that would give me the moles of acid, which means that I now know the moles of base. And if I know the moles of base and the volume I started with, I can calculate the molarity. There's a quick shortcut to do this. Okay? Again, I'm not going to teach you, I want to teach you the easiest way to do these problems. Okay? So there's no do it out in a big long format and then I'll teach you a little trick. Here's the trick. Okay? Molarity of acid times volume of acid equals moles of acid. Moles of acid equals moles of base at this special equivalence point, at the end point of our titration. Which means that moles of base times volume of base equals moles of acid times volume of acid. If you're doing any kind of acid-base reaction, typically titration type problems, molarity of acid times volume of acid equals molarity of base times volume of base. This equation is on the useful equation sheet. Okay? This equation is on the useful equation sheet. So, let's say that I had 25 milliliters of 0.350 molar sodium hydroxide. In this case, I know what the sodium hydroxide is. I know its constant volume and concentration. And let's say I have 0.1 molar hydrochloric acid. What volume of acid would I need to reach that equivalence point, to reach the point where the acid and the base have just reacted together? Well, molarity times volume of acid equals molarity times volume of base. I plugged into the equation. Now it's a simple rearrangement. Move the molarity to the other side. Solve it out.
So that's how much it would take to neutralize 25 milliliters of sodium hydroxide.
Yep. If I wanted to neutralize 25 milliliters of 0.35 molar sodium hydroxide and I had 0.1 molar hydrochloric acid, I would need 87.5 milliliters. Okay? I know that there's a lot of material to take in. Okay? I think it's better for us to do this new material today, finish new material tomorrow, and then we'll have a week and a half of nothing but practice problems. Okay? We'll do another lab to help us figure stuff out, and we'll just do problems and problems in class to keep going. Okay? The test, you'll see the test is not going to be as bad as you think. Okay? The questions and the type of thing, it's not that bad once you've practiced it some. And I know there's a lot of material you guys are learning, but we're going to have a good number of days in class, at least 4 days in class of no new material, and a full week and a half of no new material, 2 weekends and 2 holiday days as well. Okay? If you continue to keep pushing and trying the problems, you will get there, you will get it. It's just going to take a little bit of time. Okay? I know I'm dumping a bunch of stuff at you all at once. So, let's do a quick practice problem. Same basic question as what we were just asking. What volume of 0.25 molar HNO3 would be needed to react with 35 milliliters of 0.46 molar potassium hydroxide? Remember the equation I just showed you, because all you need to do is substitute the numbers in and solve the equation. I'm looking for that neutralization point. What's the special thing about the neutralization point? That equivalence point. When I mix an acid and a base, it's the point at which the moles of blah equals the moles of blah. Moles of acid equal moles of base. That's the trick. Exactly. We're trying to solve for VA. Molarity of acid times volume of acid equals molarity of base times volume of base. Same equation. Substitute and solve. Okay? Give it. Let's look at this problem. Again, the key here, don't make this problem harder than it needs to be. We know that for these to neutralize, to completely react, to neutralize, to find the end point, okay, to titrate, that the moles of acid have to equal the moles of base. That tells us that the molarity times the volume of acid has to equal the molarity times the volume of the base. That's the key, that's the trick to doing these problems. So I give you the volume of the base and the molarity. I also gave you the molarity of the acid, so I gave you 1, 2, 3 of the 4 variables in the equation. MA, VA, MB, VB. We need to solve for the volume, 64.4 milliliters. All right. I have to tell you something. Tomorrow is going to be crazy, okay? I'm going to introduce a whole lot of concepts to you tomorrow, okay? But we're going to spend some time going over them, but at some point I have to introduce a whole bunch of things all at the same time because they're all interrelated, okay? But I'm going to ask you please not to worry too much. I'm not going to give you difficult. This test is, I'm introducing a bunch of concepts that we're going to see a couple more times over the course of the year. Okay? You'll see when as we start to go through problems that it's not going to be, I'm not going to ask you to do the craziest, most difficult problems. Okay? So, here we go. Here's our last slide. I think they're open. It'll make sense tomorrow. Can we have a party? What? What?
Why is he gonna beat up little girls?
I bet we
I don't know. Look at his pants. They're like the. I don't know.
I bet we
It
can't.
was funny.